Hey there, so I'm going to show you what equilibrium in a chemical reaction looks like and how to calculate that equilibrium. Reactions can be reversible, and it really depends on the set of conditions in the chemical reaction. So if a reaction is reversible, what that means is it's a conversion of the reactants to the products, and simultaneously those products can turn back into reactants. So we call this the forward and reverse reaction. So as an example, you have sulfur dioxide gas reacting with oxygen gas to produce sulfur trioxide. And you notice how these arrows, I know this is kind of funky looking, but the arrows can go both ways in the reaction. So sulfur dioxide and oxygen can turn into sulfur trioxide simultaneously. That product, sulfur trioxide on the right side, can turn back into the reactant. So you have the reverse and forward reaction occurring simultaneously. The first condition is that equilibrium has to occur in a closed system. It also has to occur at a constant temperature. We're going to explore the temperature a little bit more later, but for now let's just say it's at constant temperature. And lastly, the activation energy of the reaction has to be low. If the activation energy is not low, if you have a high activation energy, then it's going to be really hard for those reactants to turn into products in the first place. So you have to lower the activation energy in order for the reaction to convert in the forward direction reactants to products, and simultaneously those products have to be able to convert back into reactants. All right, so as an example, we start off with X amount of reactants. So say we start off with 99% reactants and 0% product. In the forward direction, you can see that my reactants start to convert into products. At a certain time in a set condition system, aka at a closed system at constant temperature, what happens is eventually the reactants and products kind of level out. The rate at which the forward reaction occurs becomes equal to the rate at which the reverse reaction occurs. That doesn't mean that the concentration of reactants and products are equal. It means that the rate of conversion is equal. So as an example, let's just put some numbers to it. Say that 1.5 moles of reactant turn into product, simultaneously 1.5 moles of product are turning back into the reactant. So the rate is equal over time. When that happens, we say that the concentrations stay constant because you're just converting back and forth with the same values. When those reactants and products remain constant and the rates are equal, we say that that is in dynamic equilibrium. So once you reach equilibrium, the rates of the forward and reverse reaction are equal, and it is said to be dynamic. So reversible reactions, when equilibrium has been reached, is made up of concentrations of reactants and products, and we can calculate that. So let's use the example A converting to B. You notice that the arrows are a different length here. So those arrows, when you write them in a different length, actually tell you what's favored in the reaction. So if you look at this back slide, you can see that there's clearly more product than reactant at equilibrium. I would say in this situation that the products are favored in this reaction because there's more of them. So that's what this arrow is showing right here from A to B. The longer arrow shows the favor. So in this situation, the product, which is B, is favored in the reaction. Therefore, you would find it in a larger concentration at equilibrium. What does this look like graphed? Well, it's concentration over time, and what you have is you have a decrease in the reactant. Simultaneously, you have an increase in the product, and you notice where these lines cross, they start to remain constant. That point is when the dynamic equilibrium has been reached at a certain given time. Concentrations are not equal, however, they remain constant. So I'm going to show you how to calculate what's called the equilibrium constant, or the K value. So K stands for constant, and then the EQ stands for equilibrium. So we're going to calculate the KEQ, and there's a couple of rules associated with this. First rule, You cannot have liquids or solids in the reaction. If you think about it, think about a double replacement reaction in which an insoluble precipitate forms. If you're forming an insoluble precipitate, you can't take that precipitate and put it back into the reaction. It falls out of the solution, therefore the direction of the reaction only goes one way. Therefore, you cannot include it in equilibrium because it's not going to go in the reverse direction. Same with the combustion reaction. Combustion reactions are only proceeding in the forward direction. They do not reverse. Therefore, you cannot write the equation using whatever's been combusted because it's not going to go in the reverse direction. Okay, so when we're writing the equation, it's actually a relationship between the products and the reactants. So the products are going to go on top of the equation and the reactants go on the bottom of the equation. And I'll show you what that looks like in just a second. You also have to raise each concentration by the coefficient in the balanced chemical equation. As an example, so here's just a generic formula. So the KEQ, if you look at the equation, the italicized lowercase letters J, K, L, and M refer to the coefficients, which are the balanced equation. A, B, C, D are going to be the reactants and the products. So the law of mass action states that the expression of equilibrium conditions is raised to the power of the coefficient. So you can see in the KEQ equation, you have the products, which are C and D, raised to the power of their coefficient, or the balance. So you have the products divided by the reactants, which are A and B, also raised to their coefficients. So let's see an example of that. So in this example, you have ammonia, which is NH3, it's a gas. It's reacting with oxygen, which is also a gas, to produce nitrogen dioxide, NO2, and water. In this case, water vapor, because it's also a gas. So all of these are gases, therefore they can all go into the equation. If you had any solids or liquids, those could not go into the equation. So you take the product, which is NO2 and H2O, put that in the top of the equation, and then divide it by the reactants. And it ends up looking like this. You can see that they're all raised to the power of a value. Those numbers are all of the balance, all the coefficients from the balanced chemical equation. All right. So we're going to write the balanced chemical equation for an equilibrium expression for the production of ammonia. This is a really important equation, which we're going to be talking about more. So you can see that the coefficients on this are 1, 3, 2. They're all gases, so you can put the product, which is NH3 or ammonia, divided by the reactants, N2 and H2, all raised to the power of their coefficients. And you notice that N2 doesn't have anything in the equation. That's because its coefficient is 1, so it doesn't get raised to the power of anything. You notice how in the equation, the KEQ equation, all of these are in brackets. That's because eventually we're going to be able to put the concentration of each of these substances at equilibrium into those and solve for KEQ. So the brackets, remember, equal concentration, or the molarity. All right, so what does the K even tell you? What's the purpose of knowing the KEQ of an equilibrium reaction? Well, if the KEQ is greater than 1, that means the products are favored at equilibrium, and if the KEQ is less than 1, that means the reactants are favored at equilibrium. So if I calculate a KEQ greater than 1, that tells me in my reaction, in my closed system, I have a greater concentration of product than I do reactant. And vice versa, if my KEQ is less than 1, then I know at equilibrium in my closed system, I have more reactants in there. If KEQ is equal to 1, you have large quantities of both in the system, which rarely happens. Okay, so here's a practice problem on calculating the KEQ to determine if reactants or products are favored. So you have dinitrogen tetroxide, which is N2O4. It's a colorless gas. And it produces nitrogen dioxide. So this is a decomposition reaction. When dinitrogen tetroxide breaks down, it produces 2 moles of nitrogen dioxide. Well, this is an example of a reaction that's reversible. So when the 2 moles of nitrogen dioxide are formed, they can then turn back into dinitrogen tetroxide, as long as it's in a closed system. So it says a liter of a gas mixture at 10 degrees Celsius at equilibrium contains 0.0045 moles of dinitrogen tetroxide, or 4.5 times 10 to the negative 3 moles. And you also have 0.030 moles of nitrogen dioxide. So these values are at equilibrium at a given temperature in a closed system. We're going to write the equilibrium expression and then calculate the KEQ of the reaction. So you notice that the balance has already been taken care of, so there's 1 mole of dinitrogen tetroxide on the reactant side, and it's producing 2 moles of nitrogen dioxide. Those numbers are important. All right, so what do we know? We know the equation is balanced, and we know the concentrations of each of the substances at equilibrium. So you notice how I put 0.0045 moles divided by 1 liter, as well as 0.030 moles divided by 1 liter? That's because in the problem it says a liter of gas mixture. So you have a total volume of 1 liter, therefore it is moles divided by liter. That gets us a concentration, and we can plug them into the equation. So it's going to be product, which is nitrogen dioxide, divided by the reactant, raised to the power of their coefficients. So the balanced chemical equation is a 1 to 2, and the 2 belongs to the product. So you take 0.030 squared, and then you divide that by the concentration of the reactant, 0.0045, and you get 0.2 molar. This is a K less than 1. So the KEQ is less than 1, therefore you can assume that the reactants, or dinitrogen tetroxide, are favored at equilibrium. So you would find a larger quantity of the reactant than the product at equilibrium.